All right, so we have already discussed de Broglie hypothesis, and what de Broglie predicted is that the material particles have waves associated with them, and the measure of wavelength of those material particles comes out to be lambda is equal to h by mv, where h represents the Planck's constant and mv is the momentum of the moving particle. So the hypothesis of de Broglie, the predictions of de Broglie were experimentally confirmed by Davisson and Germer. That's why this experiment is also called as Davisson-Germer experiment. This Davisson-Germer experiment is the experimental verification of de Broglie's hypothesis. So you can see that there is a diagram on the board. It's a schematic diagram showing the experimental view of the experiment that was performed by Davisson and Germer. What Davisson and Germer were actually doing, they observed this wave nature of electrons accidentally. They were basically performing an experiment on nickel target to study out the reflections of electrons from the nickel target. And what happened during the experiment accidentally was that somehow there was variation in the temperature zone, and the target that this nickel that they were using, it somehow transformed into a polycrystalline solid. So while performing that experiment, they found that the reflections were showing maxima and minima. And when they observed those maximas and minimas, they predicted maybe these maximas and minimas are a result of de Broglie hypothesis, or a result of wave nature of electron. So what they did, the accidentally observed thing was then translated into a real experiment. So they performed a well decorated experiment to study the reflections of electrons on a single crystal of nickel target. So you can see that what are the equipments used in the experiment are: there is an electron gun. So this electron gun gives us the highly energetic electrons by virtue of thermionic emission. Then there is a single crystal of nickel. So the target is here. This is a single crystal of nickel, and since it's a crystal, its measured interplanar spacing is d, and that is 0.91 angstrom. And you can see the beam of electrons are emitted from this electron gun. They hit this nickel target, and there is a distribution of scatterings that are obtained out of these reflections. So the scattered radiation is detected by an electron detector, which probably is movable, so that you can measure the distribution by virtue of changing the angle of scattering. So what were the observations of this experiment? Was that they found that at some particular angle of scattering, at some angle which is noted out here as 50 degree, what they did is that they plotted the graph between angle of scattering and the intensity of scattered electrons. So when they plotted the graph between angle of scattering and intensity of scattered electrons at some accelerating voltages, at certain values of voltages that were given to the electron gun, so that there is a beam of electrons coming with different accelerations. So in doing so, what they obtained is they obtained a smooth curve for accelerating voltages less than that of 44 volts. But as this value of accelerating voltage was greater than that of 44 volts, what they obtained is a bump in their distribution. The bump was like this. So on increasing this accelerating voltage further from 44 volts, the height of this bump was found to increase. It was found to increase, and its value is found to be maximum. Its value is found to be maximum when we apply a voltage of 54 volts. So this bump or a hump, whatever you call it, this bump has a maximum height when the maximum voltage that is applied is 54 volts. And the angle of scattering is 50 degrees. So obviously this result is a result of many repetitions and many angles that have been chosen to study the scattered electrons. And it's found to be maximum at 54 volts. So if the voltage is further increased, if you have a voltage greater than that of 54 volts, now what happens to this bump? The height of this bump goes on decreasing. The height of this bump goes on decreasing, and a stage comes. And a stage comes where this bump is completely disappeared. And the typical value for that voltage happens to be greater than that of 68 volts. So you can see this bump that was not there at a voltage less than that of 44 volts. And on increasing the voltage above this 44 volts, the bump appears, and the height of this bump goes on increasing as we go on increasing the voltage. And when we reach to a voltage of 54 volts, the height of this bump is maximum. The height of this bump is maximum. So on further increasing the voltage, the height of this bump goes on decreasing, and above 68 volts, the height of this bump, there is no bump at all. The curve is same as it is observed before 44 volts of accelerating voltage. Now the point is that why there is a peak coming in the graphs. So this was explained by Davisson and Germer. This thing was explained by Davisson and Germer. They said, come on, this peak can be a result of interference. It can be the interference of waves that leads to the formation of this peak bump in the observed graph. Because at that moment of time, it was clear that whenever you allow X-ray photons to fall on a crystalline substance, the things like diffraction take place by virtue of interference of X-rays. So, which is well explained by Bragg's law. So here, the point of explanation, in order to explain the obtained curve, what was done is that they correlated the X-ray diffraction with electrons, because here the source that was emitting, it was not emitting photons, it was emitting electrons, and electrons are assumed to be the material particles. So when we assume that these electrons are also behaving like photons, they are also behaving like waves, then there should be some kind of correlation between the Bragg law that can be applied on the crystal and the wavelength that was hypothesized by de Broglie. So in doing so, what should we do in this case is that I should write Bragg law. So what is Bragg law is n lambda is 2d sine theta. As I had already written down the experimental value of d, that is 0.91 angstrom. And this theta, if you see the diagram, it's like this. Now this is your phi, this is theta, and this is also theta. So I can say that if this phi, because the peak is maximum when phi is 50 degree, I can find theta comes out to be, it must be 65. So if I presume that n is equal to 1, the lambda will come out to be 2 into d is 0.91 and sine 65. So on calculating these values, the lambda comes out to be 1.65 angstrom. So this result is coming by applying Bragg law to the current situation. If I apply the de Broglie equation and calculate the wavelength of the electrons which were predicted by de Broglie, what will be the value? What value will come out of it? In that case, I will use de Broglie equation. What is de Broglie equation? Lambda is equal to 12.27 divided by under root of V angstroms. So all we have to do is to use the value of accelerating voltage at which the maximum peak is observed. So what will be lambda there will be 12.27 divided by under root of 54 volts angstroms. So when we calculate this, we obtain a value equal to 1.67 angstroms. Now you can see the value that we have calculated for lambda in terms of Bragg law is very close to the value that we have calculated by virtue of de Broglie equation. That means the two values are agreeing with each other, very, very closely agreeing to each other. So this fact of correlation between these two lambdas indicate that electrons are behaving like waves in this experiment. That's why this hump, that's why this bump is observed in the graph, verifying the fact that what de Broglie predicted is right for microscopic particles, is right for atoms, is right for molecules, is right for electrons, neutrons, and protons. So here comes the experimental support to what de Broglie predicted. So this experiment gave the understanding to the then people out there that the material particles like electrons can also behave like waves under certain circumstances.